After learning the different types of stresses that may exist within a structure, for example, normal stresses, shear stresses, and bearing stresses, and so on, what we are going to do next are study different loading conditions, right? And then based on these loading conditions, what we are going to see is that what are the different types of stresses these loads induce within the structure. So today we are going to start on the new topic on axially loaded structure. What it essentially means that if I have a structure and this is the longitudinal axis of this particular pen which I am holding, and if I am applying the load pulling or pushing, right, these loads act along the longitudinal axis. So these are the axially loaded structures. So it acts along this particular axis, so hence the name axially loaded structures. Now you might be wondering that if I have a structure that is axially loaded, for example, the ones that you see over here, this load acts along the longitudinal axis, this acts along the longitudinal axis as well. You might probably be thinking that this is easy because this is only going to induce normal stresses. But through this chapter or through this topic, what we will see is that it really depends on which point of the material you are looking at or which point of the structure you are looking at and how you are looking at it, right? Now, analogically, the stretching and the contracting of these structures under these axial loads can be mimicked in terms of a spring over here. You have studied springs in your +2 and the entrance examinations. So essentially, if you're pulling it, you will have the stretching of the spring or the contraction of the spring if you're pushing it, right? But always remember that the mechanism in which a spring stretches or a spring contracts is actually vastly different. For example, here in these ones, this load causes a direct stretching and a direct contraction, and the different smaller elements within this particular rod over here, or this one for this matter, undergo an expansion or contraction. As opposed to that, in springs, actually the loading mechanism and the load transfer is quite complicated. So this load essentially traverses through these coils of the spring. So the figure of the spring here is just as a demonstrative example. The truly axially loaded structures are structures which are of the kind of the ones that you have here, or practical examples of your building columns and so on, right? So now just getting into this particular topic, so first what we are going to look at are essentially prismatic bars. So remember, if you don't remember what prismatic bars are essentially the bars in which the cross section remains same along that particular length, right? So, and that cross section can be anything. That cross section can be it can be a solid cross section, circular, it can be a rectangular cross section, it can be a hollow cross section, and so on. So things which we are going to derive are valid for any kinds of cross section as long as the bar is prismatic. That means that this cross section is same across that particular length. For example, this pen is probably non-prismatic because here you have a shorter cross section, and towards this particular end you have a thicker cross section, you have a thinner cross section here. This is a non-prismatic member that you see over here. As opposed to that, this sponge is probably a prismatic section because all across it has the same area of cross section, right? Now, coming back to what we had actually studied until now, is that if we have a particular rod, something like this, and if you're pulling it with this particular force P over here, you will undergo some amount of deformation delta, right? Now, as you can understand, this is a clamped end over here. So as a consequence of this support being there, we will of course develop some reaction, right? And the magnitude of the reaction will also be equal to the applied loading P over here. Now, regardless, remember that what we had derived is that from the previous topic. So we have derived the expression for the stresses and the strains, right? And also we know that how stresses and strains are related, right? So if we take each of these one by one, what we have kind of learned is that my sigma is equal to P divided by A, right? This is for the stress. And for the strain, which is designated by the Greek symbol epsilon, we have epsilon equals to delta divided by L. We know these two quantities, right? And for within the proportionality limit, within that linear region where Hooke's law is still valid, what we know is the relationship between sigma and epsilon is that your sigma equals to E, the Young's modulus or modulus of elasticity, times epsilon over here, right? Now if I do a little bit of rearranging, let's see what we get. So we can write sigma as P divided by A. This will be equal to the Young's modulus times delta divided by L, right? So this further gives me, if I do a little bit of rearranging, what I get is my deformation delta, which is essentially your this particular quantity over here, becomes equals to P times L divided by A times E, right? So this is an extremely important relationship that you have, that delta is equal to PL divided by AE. You will use this particular formula through and through when you start to solve problems of structures under axial load, right? Now in this particular expression that I wrote over here, you see the terminologies. You have the load P, right? You have the length L, right? And A, which is the area of cross section, and E is the Young's modulus of this particular material, or whatever the material this bar is made of, right? Now just going ahead, and if we have to just write this formula again, what we have is what we just derived, that what we just derived is delta equals to P times L divided by the area of cross section times the Young's modulus E, right? Now take a look at this formula, especially the denominator. There is a particular terminology for the denominator that we have over here, this particular guy, right? This guy is known as the axial rigidity, right? Why is it called axial rigidity? Let's just break up the words. Axial because you're dealing with axial loads, but why rigidity, right? Now if you take a look at this formula, right, for a bar for a given area and a given area of cross section A and the Young's modulus E, if you bump up the area, your deflection becomes smaller and smaller, and if for a particular material, if you take a different material with a higher E, then this delta also becomes smaller, right? So these terminologies, is A and E together, as it goes higher and higher, it makes the structure more and more rigid. Essentially your deflection becomes lesser and lesser, right? So this particular guy over here, this is known as, these are just terminologies, this is known as axial rigidity, AE, right? Now a couple of derivatives from this particular formula, which you will make use of maybe now or in some of your future courses. So if I take this particular formula again, and if I write it in a slightly different way, that your delta equals to L by AE times P over here, what it essentially means that if my P is equal to 1, right, if my applied load is equal to 1, the deformation I am going to get is L over AE, because it is L over AE times 1, right? So this quantity L over AE is nothing but deformation under unit load, right? And it's also known as flexibility. Designated by the symbol F, right? Now again, if I rearrange this a little bit and bring P to my left and the rest of the quantity to my right, what I essentially get is P, I'll write this again, I get P equal to AE divided by L times delta, right? Now similar to between these two is that how we expressed when P equals to 1, what is the delta here. When delta equals to 1, your P is AE divided by L. So what does it essentially mean? That means that this is the load, AE divided by L is the load to produce unit deflection, right? So if I have to write it, so this is the load for unit deflection, and this is known as stiffness. K. Right. So as you can tell that K is equals to 1 divided by F, right? So essentially stiffness is inverse of the flexibility, right? In real life as well, if someone is flexible, that means a stiff person, you know, has an opposite nature compared to someone who is flexible, right? So this is also kind of an important relationship later in your even in this course or some of your future courses, that you will see that, you know, these relationships pop up. For example, when you do structural analysis or structural mechanics, you will see there is a flexibility method and stiffness method which uses some of these kinds of formulations which are there, right? So now that we have the basic groundwork done, for example, this particular guy over here, right, that delta is equals to PL divided by AE, let's look at one example of how we are going to make use of this particular formula to solve a particular problem.